Hello everyone. On this video we will be covering triple integrals. Alright, so what if we let f be a continuous solid, or be continuous rather, on a solid region that we will call Q. And let's say that's defined by x is between some value a and b. Let's say y, that's between two x functions. We'll call that our first function of x and our second function of x. And z between two functions of x and y. So we'll call this our first function of x and y and our second function of x and y. Okay, where we know that our function number 1 and function 2 of h and our two g functions they're all continuous. Okay, if that's the case, then the triple integral over the solid region Q of f of x, y, z with respect to the volume is equal to the integral from a to b, the integral from h number 1 to h number 2, and the integral from g number 1 and g number 2 of f of x, y, z, dz, dy, dx. Okay, so quick note. You're looking for just the volume of the solid region of Q. Volume solid region Q is given by volume of Q is equal to, that's just the triple integral over Q and just dv. You don't have to put in your f of x, y, z. Alright, so if you are still writing this, feel free to press pause, but we're going to go ahead and jump to our first example. Alright, so for example, what if we just want to set up the triple integral for the volume of a solid in the first octant bounded by the coordinate plane or the coordinate plane. No, coordinate planes. And the plane. z equals 4 minus x minus y. All right. Now think about this one is we're not going to solve it. We're just going to set up the integral. Okay, so this one's a do not solve. We're actually going to solve one a little later, but this one's just the setup. Okay. So you don't have to draw the 3D plane on this one, but sometimes helps just to draw your X, Y, and Z axis. Okay. Now this, where X, Y, and Z are all positive, that's your first octant. That's where X is greater than or equal to 0, Y is greater than or equal to 0, and Z is greater than or equal to 0. Okay, so now we have to find the boundaries for our X, Y, and Z. Okay, now if we're looking for boundary for Z, that's pretty much given to us because we know that Z is greater than 0 and it stops at that plane. So we know that Z is actually between 0 and 4 minus x minus y. Okay, so we have our boundary for Z. Now we have to find the boundaries for y. Move that over a little bit. Okay, so we see here also that, I'll move that underneath it, y is greater than or equal to 0. Alright, so once we see that y is greater than or equal to 0, that means we're looking at just along y, which means we can pick where z is equal to 0. Because we're looking really at just the xy axis, really. So we're looking along y. Okay, so if z is equal to 0, that's 0 is less than or equal to 4 minus x minus y. So if we add y to both sides, we end up with y is less than or equal to 4 minus x. So that gives us the boundary of y being between 0 and 4 minus x. Alright, so now looking at our third boundary, our boundary for x. We can look right here again. If we notice here, we're just looking for our boundary for x. Some value between x here and x there. Okay, which means if we wanted, we could go ahead and make y equal to 0, because we know they're all greater than or equal to 0. So if we make y equal to 0, we can focus on just the x. Okay, so if y is equal to 0, that would give us 0 is less than or equal to 4 minus x. Add x to both sides. We end up with x is less than or equal to 4. Okay. Now we add that with the fact that we know that x is greater than or equal to 0. We get the boundary of 0 is less than or equal to x, less than or equal to 4. Okay, so once we do that, all we have to do now is just set up our triple integral. Okay. Volume of the solid region, remember that's equal to the triple integral from Q with respect to the volume, which is equal to the integral from 0 to 4, the integral from 0 to 4 minus x, and the integral from 0 to 4 minus x minus y. Okay. Now, remember when you have your internal, that's with the bound. That's the boundary for z. So that means your dz is going to have to go first. Because remember, we're solving from the inside out. So the dz goes first since that's the boundary you use. Which means the y goes second since that's the second boundary. And the x goes last since that's the boundary on the outside. Okay, so we have our setup for our triple integral. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Alright, so let's say, for example, what if you want to set up the triple integral for the volume of the solid bounded by the paraboloid z equals 9 minus x squared minus y squared, and the plane z equals 0. Alright, so we already know our boundary for z. It gave us that first of all. Okay, so our boundary for z is of course going to be between 0 and 9 minus x squared minus y squared. Okay, so now we look at our boundary for y. Okay, so again, we know that looking at z equals 0, we made z equals 0. That would give us 9 minus x squared minus y squared. That's greater than 0. Or 0 is less than that. Okay, so if we add y squared to both sides and square root both sides, we'd end up with y is less than or equal to plus or minus the square root of 9 minus x squared. Okay, so we have our boundary for z and our boundary for y, which you can also rewrite this as negative square root of 9 minus x squared less than or equal to y is less than or equal to the square root of 9 minus x squared. Okay, so now we find our boundary for x. Boundary for x. We'll use that one and kind of erase this one since that's the one we're going to use. Okay, so our boundary for x, of course, we know that for x, 9 minus x squared has to be positive because if it's negative, we're dealing with complex numbers and we're only dealing with real numbers. Okay, so we know that 9 minus x squared is greater than or equal to 0. Or you can just rewrite that as x squared is less than or equal to 9. Okay, square root both sides. We have x is less than or equal to positive or negative 3. Okay, so that gives us the boundary of x being between negative 3 and 3. Okay, so we go ahead and we write out our triple integral. Okay, or volume is equal to a triple integral, which will become the integral from negative 3 to 3, the integral from negative square root of 9 minus x squared to positive square root of 9 minus x squared, integral from 0 to 9 minus x squared minus y. Oh, minus y squared, sorry about that. Okay, so again, since the z is the closest to the center, I'm going to go dz. Y, by that being second, I'm going to do that second. And with the x boundaries being on the outside, we go ahead and put that on the outside. Okay, so we set up our triple integral. Okay, remember, we didn't have to solve it, just had to set it up. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Alright, and this involves changing the order of integration. Alright, so let's say for example, if we want to list the 6 possible orders of integration, for the triple integral okay, so let's say we have the triple integral q xyz with respect to the volume over the solid region. Q is equal to xyz such that x is between 0 and 1, y is between 0 and x, and z is between 0 and 3. Okay, so we want to set up all 6 of our orders of integration. Okay, so all that means is that for our respect to the volume, we want to find the order of integration dz, dz, dy, dx, and dz, dx, dy, and dy, dz, dx, dx, dz, dy, dy, dx, dz, and dx, dy, dz. Okay, now it doesn't matter which one you do first. You just have to find all 6. Those are the 6 possible orders you have. All right. So, starting with our first order, if you remember, well, this is where I always start, just to have some place. Remember the formula from A to B, H1x, H2x, G1, xy, G2, xy, of f of x, y, z, dz, dy, dx. Okay, that's just the formula. Okay, so that's why I usually pick that to go first. But if you wanted to, you could have switched those around, but we're going to show you how to switch all of those around. Okay, So just our dz dy dx, you see that's going to equal the integral, since dx is on the outside, we're going to go from 0 to 1. dy is on the inside, so we're going to make that from 0 to x. And dz is on the inside, well, is on the far left, so we're going to make that from 0 to 3. Okay, so that's x, y, z, dz, dy, dx. Okay, so we have our first one. We can go ahead and check that off. Okay, so now we're going to create our second order of integration. And really, this is just a matter of seeing what you have and how you can manipulate it around. Okay, so if we look at the boundary surfaces, okay, we see here that x is greater than 0, but x is less than 1. Okay, so we're just going to mark that down. Greater than or equal to 0, x less than or equal to 1. Okay, we also see that y is greater than or equal to 0, and y is also less than or equal to x. Okay, so we see here that z is greater than or equal to 0, and z is less than or equal to 3. Okay, so how can we use that to change our our order of integration? Okay, now the thing is, you just have to pick one that you want to put in that order. Let's say if we pick this one, our dz, dx, dy. Okay, so dz, let me move that down a little bit. Okay, so dz, dx, dy. Okay, and our x, y, z. So now we just have to pick our integration values. Okay, so how do we do that? Look at these. Okay, so we see here that x is less than or equal to 1, but y is less than or equal to x. Okay, so if we start on the inside, our z boundaries are just constants, so you can take that from 0 to 3. But remember, when you plug in your x value, you want to go from your x value and still have a y variable left, even if that y variable is a constant. But in this case, we won't need a constant, because for our respect to x, we see that y is less than or equal to x, but x is less than or equal to 1. Okay? So, for our respect to x, we can make that from y to 1. Okay? We see also here that because y is less than or equal to x, and x is less than or equal to 1, and y is greater than or equal to 0, you can kind of combine all three of those to make y 0 is less than or equal to y. And since y is less than or equal to x, and x is less than or equal to 1, that means y is also less than or equal to 1. So, let me lower this a little bit. That gives us 0 to 1 for our y. Okay, so this is our second. Now we're going to look at our third boundary surface. Okay, so we'll do the dy, dz, dx. Go ahead and check that off. Okay, so we have dy, dz, dx of x, y, z. So now we just have to figure out our boundary surface for our integral. Okay, so since dy is first, we want to make sure that when we solve with respect to y, we have dz and dx variables still there. Okay, so we see that y is greater than or equal to 0, and y is less than or equal to x. We can get the boundary surface of y being between 0 and x, which is actually what we started with anyway. Okay, so we can go from, for the respect to y, from 0 to x. With respect to z, that can actually remain a constant between 0 and 3. And our x can be between 0 and 1. Because remember, that's our final integration. So we just want to be able to plug in our variable, our constant. All right. Okay, so we're running out of room here because this is our third. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and continue this on the next page. Okay, so looking at our list, the fourth one, we're going to do dx, dz, and dy. Go ahead and check that off of our list here. Okay, and that's x, y, z. Okay, so remember, the first thing you want to do is integrate with respect to x. Okay, which means when you integrate with respect to x, you still want to have z and y variables left. Okay, so let me move that a little closer. Okay, so if we integrate, we have to find out boundary surfaces. Okay, so if you remember, x is greater than or equal to y, and x is less than or equal to 1. Okay, so that means that y is less than or equal to x. Y is less than or equal to x, and x is less than or equal to 1. We can just go ahead and move that just like that. Okay, which, if you remember, we already had here. So a lot of these we're going to go ahead and be able to reuse. All right, so that means you're going to go, for our x, we're going to go from y to 1. Okay, now for our y, we're going to actually take that. If you remember, if you go back to this one, oh, I thought we had that, we didn't use that yet. So for our y, you can take that actually from 0, or z, sorry, that's why it's working out, or z, you can take that from 0 to 3, and then we go to our y. Okay, so we see here for our y, that since we have, kind of circle that one, 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to x. Okay, that lets us know that y is less than or equal to x, and x is less than or equal to 1, which means that, kind of running out of room, I don't want to take up this whole page, but y is less than or equal to 1. And we also know that it's greater than or equal to 0, so we can put that there. So we can use this one. Y is between 0 and 1. Okay, so that gave us our fourth order of integration. All right, so for our fifth, we kind of draw a little separator here. let's say we decide to find the order dy dx dz for our x, y, z. So now we just have to find our integrals. Okay, so again, since we're doing respect to y first, we're going to go back because we have to have a dx and a dz when we integrate with respect to y. So we're going to go back to our first page and use the fact that y is between 0 and x. Okay. Now, going back to right at the very beginning, if you look on the first page, x is between 0 and 1. We're just going to go ahead and use that one. And our integral with respect to z, that could just be the same, 0 to 3. Okay, so that's our fifth order of integration. And for our sixth, that's dx, dy, dz of our x, y, z. Okay, so now, again, since we're going to do with respect to x first, remember you still have to have a dy or dz after you integrate with respect to x. So we can go ahead and use the fact that y is less than equal to x, less than equal to 1. So x goes from y to 1. Our dy, we can use the fact that y is between 0 and 1. Where did we use that one? If you look back on the first page here, we use that already. So we can go y is between 0 and 1. And our dz, we can make that between 0 and 3. And that's our sixth. Okay. Now these are all equivalent, so it doesn't matter. As long as you list the possible orders correctly, these should all give you the same answer. So these are all equivalent triple integrals. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so what if we wanted to evaluate the triple integral from 0 to square root of pi over 2 x to square root of pi over 2 from 1 to 3 sine y squared dz dy dx. Okay, so a heads up, we're actually going to do this one twice. Okay, because currently the way this is set up, it will cause you to have to do a lot of extra work. Okay, so let's say y solving in its current form is not the most convenient. Okay, so we're going to go ahead and solve this one in the current form. Okay, so just to rewrite it, so from 0 to the square root of pi over 2, x to the square root of pi over 2, and from 1 to 3 of sine y squared dz dy dx. Okay, so if we integrate with respect to z, this is treated as a constant. So we'll go ahead and make that z sine y squared And go from 0 to square root pi over 2. And go from x to square root of pi over 2. And we can make that z sine of y squared. We know that's from 1 to 3. So z equals 1 to z equals 3. Okay. So if we plug in our 3, we have 3 sine y squared minus 1 sine y squared. We just end up with 2 sine y squared. So dy dx. So we end up with the integral from 0 to square root of pi over 2 from x to square root of pi over 2 sine y squared dy dx. And this integration is where we're going to run into our trouble. Okay, you're probably looking at it going, oh, okay, that's not bad. It's just a little u substitution. No, that won't work. Because what we want is if we make u equals y squared, for our du to equal 2y dy. Okay, so if you notice here, that 2 times the integral, I'm not going to worry about putting those down, of sine y squared dy is not equal to the integral of sine y squared 2y dy. So here we have our sine of u du. I could have kept that up. So sine of u and our du. Okay, so in this current form, it can be solved, but it will probably take you about, give or take, that's assuming there are no mistakes made, about 30, 45 minutes. You can probably search and find a video somewhere, and it will literally take you about a half hour just to solve this one. Okay, so what we're going to do, since we know that since the integral 2 sine y squared dy can get very complicated, okay, we will change the order to make it easier. Okay, because remember, even if we change the order, as long as we change the order correctly, it will give us the exact same answer. So why not make the problem a little easier to get the same answer that the hard work problem will give us? All right, so what we're going to do is we're going to continue this on the next page. So if you are still writing, feel free to press pause, but we're going to go ahead and do this same problem on the next page. Okay, so we're going to evaluate the integral from 0 to square root of pi over 2 from x to square root pi over 2, and from 1 to 3 for sine y squared dz dy dx. Okay, so if you notice here that our z would have to go from 1 to 3. Okay, so 1 is less than equal to z less than equal to 3. You know our dy, so that means y will be between x and square root of pi over 2. So x is less than equal to y, less than equal to the square root pi over 2. We know our dz, or our z rather, our x, since I wrote that twice, that's why it's confusing. dz, dy, dx. There we go. Our x is between 0 and square root of power of 2. Okay, now kind of switch it up a little bit. We know 0 is less than or equal to x, and x is less than or equal to y, just using those two. So that means 0 is less than or equal to x, and x is less than or equal to y. Okay. Now what else do we know? And we know that 0 is less than or equal to x, x is less than or equal to y. We also know that y is less than or equal to square root of pi over 2. Okay, so we have boundary number 1 for x. To find our new y boundary, we just make y between 0 and square root of pi over 2. So 0 is less than or equal to y, less than or equal to square root of pi over 2. Okay. Now the z, we can just keep it like that. That's not really hurting anything. So now we just have to pick our new order of integration. Okay, so how about we just switch up those two? New integration order. Okay, so we'll just pick dz, dx, dy. Okay, so that means that our new boundaries will be z is between 1 and 3. We're going to keep that one. So we have our z between 1 and 3. So 1 is less than or equal to z, less than or equal to 3. Our x is between 0 and y. So 0 is less than or equal to x, less than or equal to y. And our y is between 0 and square root of pi over 2. 0 is less than or equal to y, less than or equal to square root of pi over 2. Okay, so that means, since we're looking at the new integration order dz, dx, dy of sine of y squared, starting from the center, our z, we know that's from 1 to 3, just from this. We know our x is from 0 to y, and we know that our y is from 0 to square root of pi over 2. Okay, so once again, we start at the center. We really get because we only changed these last two, we'll get the same thing we got on the previous attempt, but we'll still go through the steps from 0 to y. Remember, that will be z sine y squared. And that's from 1 to 3 dx dy. And if you remember, you plug in the 3, then you minus the 1. You get 3 sine y squared minus 1 sine y squared. We get the integral from square root 0 to square root of pi over 2. From 0 to y. And we have 2. Well, we don't really need the bracket. 2 sine y squared dx dy. Alright, so just like we did with the z, we integrate this with respect to x. And we can go ahead and just bring the 2 out. So we have 2 times the integral from z to square root of pi over 2. That would be x sine y squared. And that would go from x equals 0 to x equals y. So x equals 0 to x equals y. And still have our dy. Okay. So if we plug in y, we get y sine y squared minus 0 times that. So that's just going to end up being the integral from 0 to square root of pi over 2 of 2y sine y squared dy. Okay. Now, if you remember, the biggest problem we had previously was that our u substitution wouldn't work. So here, if u is equal to y squared, our du is equal to 2y dy. Okay, so if we just switch that right on around, we have the integral from 0 to square root of pi over 2 of sine y squared times 2y. I'm just going to move that over. 2y dy. We have our integral of sine of u du, which is equal to negative cosine of u. So that's negative cosine of y squared, and that's from 0 to square root of pi over 2. Okay, so exactly what we were looking for before, we were able to find it just by switching it around, and we didn't have to work on it for another 40 minutes or however long that last one would take. Okay, so if we plug in our square root of pi over 2, square root squared, those will cancel out, so we just end up with pi over 2. So that's negative cosine pi over 2 minus negative cosine of 0. Okay, so since cosine of pi over 2 is 0, that just disappears. So that's 0 minus negative cosine of 0 is 1. Our answer is just 1. And there are no two more irritating answers after all of this work than 0 and 1. But this is the case. That's our answer. All right. So every once in a while, you will have to, well, you won't have to, but if you want to save yourself a lot of work, you will change the order of integration for some of your triple integrals. And this is how you would do it. All right. So hopefully this video made sense, and I'll see you on the next video.